So in the previous section, we had the GPT model generate text, and then we as humans, we looked at the text and we saw, oh, this is actually not very good text. So in this section, we are now going to implement a way we can measure this quality of the text more numerically. And so for this, we are going to calculate the text generation loss. So a loss function is a measure, in this case, how good the generated text is. And then we will be using that to optimize, or more precisely to minimize the loss, to optimize the generated text later in this chapter. For now, we are implementing the loss itself, how we measure this. And the technical term in this case for the LLM training of the loss function is the cross-entropy loss. So cross-entropy loss is a loss function that helps us measure the quality of the generated text. And we will also briefly talk about a related measure, the perplexity of a text. You might have heard perplexity before. We will also briefly talk about how perplexity is related to cross-entropy. But yeah, we will tackle this one step at a time. So just to briefly go back to a figure that I showed you in chapter 4, at the end of chapter 4, we had this figure where we went from token IDs to these tensors. And then we computed the logits and the probabilities of the last tensor. And so this was essentially for generating the next token. Now, what we are interested in is not just generating the next token, we are interested in measuring the quality of each generated token. So what we are now analyzing is this whole thing, because for each input token, the LLM generates a vector, and this vector contains information about the following token. So remember in chapter 2, we set up the inputs and the targets, where the targets were shifted by 1. So we had, if we have something like hello, I am as our inputs, the targets would be comma, I am a, right? So then the output here, this comes from the first token, this should be able to generate the comma token. Maybe if this is too complicated, let me show you a simpler example. So let me maybe give you a concrete example where we have inputs and targets. So what I'm trying to say is if we have token IDs corresponding to some input text, for example, every effort moves, if we convert this into tokens, we will get these tokens here. This is using the tokenizer. And the targets, so here we have the corresponding targets, are shifted by 1 position. So this would be effort moves, and then the next token we want to generate. So we have this shifting by 1 position, similar to what we have done in chapter 2. Okay, so, and we want to know if the model generates tokens, we want to now measure how good are those for predicting this next token. So we'll get there maybe one step at a time. So here I'm showing you one input and then the targets. This is what we want the model to generate. Here we have a second input, just so that we have multiple examples. And here the second input is I really like, and then the targets for that one would be, for example, really like chocolate. So really like, so because it's shifted by 1 position. Also, I chose these examples so that this one has nothing to do with this one, because I want to highlight when we have a batch of multiple inputs, these rows are unrelated to each other. So the relationship is between the first row here and the first row here, and then the second row here and the second row here. Because the inputs correspond to the targets, but there doesn't need to be a relation between the first and the second example here. If you are pre-training, you could, for example, chop up your text with a sliding window approach that we have done in chapter 2. In that case, they kind of relate to each other, but it's not necessary. They can be totally independent, like shown here. Now let's generate the logits. So what we're doing now is we are generating these outputs here, the logits. I can also maybe just show you the figure we looked at earlier in the previous section here. So what we have is the input text into tokens, and then we generate this output tensor, these logits. So let's do that. So here, similar to what we have done before, we generate the logits. And yeah, let's just take a look at the shape of these logits. So what we see here is it's 2 by 3 by 50,257. Where does this number come from? So 2, because we have in the inputs 2 rows. Each row has 3 tokens. So that's where the 3 comes from. And each of the logits is a 50,257 dimensional vector that corresponds to the vocabulary size. And then we had the step where we converted these into these probability tensors. We had the softmax function on the logits, like this. And this one, let's just take a look at the shape. And this one has the same dimension here. We haven't extracted the last tensor or anything like that. For this one, we're looking at every tensor now. So yeah, so maybe to see this more clearly, I should have a figure somewhere here. So we have an input here. Every effort moves, which we convert into token IDs. I'm using a different vocabulary here. I'm not using the 50,257, so that allows me to fit it into one slide, because 50,000 would be quite long. So we have these token IDs we get from some input text. And then each token ID is converted into the logits and then the softmax, the probabilities. So here you can think of this row here as what we have here. So if I maybe show it to you here. So we have 2 input examples, so this one and this one. Each one consists of 3 rows, 1, 2, 3. And each row here is, so it's kind of wrapped around the line, but this is, you can see it's dotted out, it's 50,000 dimensions. So instead of looking at 50,000, because it's very long and then we had to dot out these lines, I'm using a smaller vocabulary so that everything fits into one line. And one thing about the softmax function, if you recall, these sum up to 1. So what we're looking at here, the vocabulary 0, 1, 2, 3, 4, 5, 6. So we have 7 entries. So there should be 7 entries here, 7 probability scores. And the first value tells me for this token in the input, I have a 10% probability to generate A. I have a 60% probability to generate effort. I have a 20% probability to generate every. I have a 5% probability to generate forward, and so forth. So these give me the probabilities of the next token that is likely. How probable is this that this is the next token? And so the model learns during the training later to give high probabilities for the true token that we want to generate. The true token or the target token is what we have in our targets. So you can see every effort moves you. These are our targets. These are our inputs. We want the model to generate the targets, so the shifting by 1 position. So here in this case, we want a high probability for the target. And the target, effort, so if I go back here, we had the inputs, every effort moves, and the targets. Now I want for every, I want a high probability for effort. And for effort, I want a high probability for moves because it's shifted by 1 position. So here I want a high probability here. We have a 60%, it's the highest probability. If I look up the index position, so 0, 1, 2, 3, 4, 5, 6, 0, 1. So this is index position 1, and this corresponds to effort. This is good. This is what we want. Now, next, for the second token, I look up again the position. What is the highest probability? Oh, it's this one, 35%. It's the highest one. It corresponds to token, so index 4, token ID 4. What is token ID 4 in my vocabulary here? 4 corresponds to moves. So I have this inverse vocabulary. You can see this is like flipped and it's easier to look up. So 4 corresponds to moves. So I generate moves. Next, moves as my input token. I look at my probability tensor, Where's the highest probability? Oh, here. What is this? Oh, index position 5. 5 corresponds to U. Okay, I generate U. And this is how we go from probability scores back into these here. And if you recall from the previous chapter 4 video, when we implemented the generate text simple function, we used the argmax to determine this index position. It maybe looks like a highly complicated figure, but all that there is happening here is we have a vocabulary where we go from token IDs to, so from tokens to token IDs, we get the softmax, and then we go with the argmax backwards from probabilities to token IDs and then back to text. Okay, so it was a lot of information maybe, hopefully not too complicated. Now we have these probas here. The probas, short for probabilities, are these values here, these rows you can see. They're just a bit bigger because we have this 50,257 dimensional vocabulary instead of having just 7, right? So yeah, that is what we have so far. Now, let me show you the code to convert this back. So here, argmax, like I mentioned before, argmax is going from probabilities to these indices. So these indices, I'm just showing them here twice, it's just the highest position of the position of the highest probability in each of the cases. So this gives me the token IDs of the highest probabilities. So for the first token, it's 16,000 in the vocabulary and so forth. These numbers are higher because, like I mentioned before, this is a smaller vocabulary for illustration purposes. Okay, next, so we have these token IDs. Next, we can convert these token IDs into text, similar to what we have done before. And so here I'm indexing, just looking at the first one, the first example. So we have 2 examples in text, 0 and 1. For simplicity, I'm just looking at one of them here. So you can see I'm just looking up target 0. I'm just looking up this here. Every effort moves you. It's just a look up. And now I'm looking up what has our model generated for these targets. If I'm going through this one, ideally what we want is that the generated outputs match the actual targets. So ideally, we want the model to generate this. But when I'm looking at the result, it writes something like ARM T Netflix, which does not make any sense. And this is because we haven't trained the model yet. After the model training, ideally, the model will generate this text as similar to the targets, basically. Okay, so this is where we are so far. Next, here I'm just focusing on the first example, similar to here, just assigning it 0. Why? Just to keep it simple, that we don't look like that we don't mix them up. So let's just blend this out for now. We can focus on this later. And so what I'm looking at here is the probabilities for the first example. And then I'm looking at these 3 tokens. So we have 3 tokens in the input, 0, 1, 3. And similarly, I look up the corresponding targets for that one. So here, what you can see now, when I said targets, I'm meaning the IDs. So for each of the 3 token positions, I'm getting the target indices. So I'm looking up, maybe one step back here. So here I'm looking up the highest probabilities because that is what we are generating. Now what I'm looking up is what should be, what are the positions of the target IDs. So here it's the same. So the highest position is the position of the target ID, because the target ID is happens to be every effort moves you if a model generates the correct thing. So we have 1, 4, and 5 as the correct target IDs in this case, and they correspond to the highest positions. But what if, I unfortunately don't have a figure on this, but what if our model is not correct, right? So I'm looking up in this first vector what is the target ID? 3,626 for the first row. What is the probability in this one for this position, right? Because that is the one that we want to maximize. So I'm looking up in this first row, what is the token ID 3626? And then I'm doing the same thing for 6,100. I'm looking up where is, or what is the probability corresponding to position 6,100. And then in the last one, 345, what is the probability at position 345 in this whole vector here? And so that's what I'm extracting. So all of them are very small numbers. They are very close to zero. That's because the model is not trained yet and because we have a very large vocabulary. And in our ideal case, what we want to do is we want to increase those ideally to be close to, let's say, something like 90%. And that happens during training, so that the model learns to associate the generated probabilities corresponding to the text targets to be very large values. Now they're very small, but we want to make them very large. Here we can do the same thing for the second text. So again, very small values, and we want to make them very large, basically. And so in order to make them large, we have to measure this numerically, how good this is, basically. So for that, it's a multi-step procedure. So we first compute the logarithm of all token probabilities, and I can share this later. I have a whole lecture on why log probabilities. It will make it a bit simpler during optimization. There's something called maximum likelihood. If you've never heard of this, maybe don't worry about it. I will just do it more conceptually here, but optionally I can share a lecture on it. The idea is essentially that we turn the multiplication into a sum in the maximum likelihood, but different topic maybe for a statistics lecture. Here, so just think of it maybe for numerical stability, or maybe I can just show it to you if you are curious. And so it's not the right one. So if you go to my website, sorry, browser autocomplete here. If you go to my website under more, I should have courses here where I taught a statistics class back in the day when I was a professor here. And I should have this whole lecture here on multinomial logistic regression and softmax regression, where I go over all these things more slowly and computing the cross entropy and so forth. So for here, maybe just think of it as a thing to make it numerically more stable. So we are computing the log probabilities. We are taking the log, and what we are doing is we are taking, so we are first concatenating those two, because here they are separate, but we want to concatenate them, so to have them all in one, because then it's easier to apply the same computation. We don't have to apply it separately to two different tensors and so forth. So we're just combining it into one tensor. And then we apply the log. So here, so we turn this from very small values into now these negative values. So the smaller the value, the more, the higher the negative number here is, for example. So that's what we are doing here. And then we can compute the average. So we can do torch dot mean. Oops. And yeah, we provide the log probas as input. And you can see we get a value of minus 10.79. So that's the average log probability. And then what we could do is we can multiply this by -1 to get a positive number. And this is, so it took us a long way to get here, but this is the so-called cross entropy loss. And during training, our goal is to make this close to zero. That's our goal, basically. We want to get this number very close to zero. And if this number is close to zero, that means these values are close to zero, which means that these values are, so the log values is the same. Let me get rid of this, it's less confusing. So again, so we want this to be close to zero, which means that these are basically very close to 0, which then means that these are very large values, because when you look at this, let's do a torch.log, let's do 0.99. You can see this is a number that is it's close to 0, basically. So our goal is essentially to make the probabilities very large. So ideally 1, which will make those close to 0. And if we have a very small probability, this will be a very, 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 very negative number, like minus, I don't know, minus a very large number. So here, minus 36, for example, here. Yeah, so our goal is essentially to get those close to 0, which means that the probability will be close to 1. Because if this is close to 1, this will be corresponding to the correct target ID. Because again, right now we got the target ID, the probability corresponding to the target ID. We want to make it large to make sure it gets selected by the torch argmax. So we want to make sure we have the large values at the right position in each case here. Okay, so, and this is where this cross entropy comes from. Again, like I mentioned before, if you want the more nitty-gritty detail, you are free to watch these videos. It's a lot of videos here, I think. But it's not really necessary, to be honest. I think all you need to understand is that we are just measuring how good our generated outputs are, and we want to get this number close to 0. Now, this is also a lot of steps, right? So we have quite a few steps with a softmax here. So first the logits, then the softmax, then the argmax, and then the log, and then the -1. And there is a quicker way in PyTorch, and there is actually this torch.nn.functional.cross entropy function. Maybe I have a figure on this. Let me scroll down. One moment here. So what we have done so far is we went from the logits to probabilities to get the probabilities corresponding to the target token IDs. We converted them to log probabilities. Then we computed the average, and then we computed the negative log probability. So just in a more cleaner layout, these are the steps. And you can see that's the same number we got. We applied these different steps one at a time to get the cross entropy loss. So the cross entropy loss is a synonym for negative average log probability. It depends a bit on where you come from. Like if you are a statistician, you would probably say negative average log probability. If you are a computer scientist who studied information theory, you would probably say cross entropy. So cross entropy is just a different word for this negative average log probability. It just happened that both fields independently discovered this measure or derived this measure. And in PyTorch, this is called cross entropy because it's more computer sciencey, deep learning, machine learning package. Yeah, in PyTorch, we can also compute this. So there's one trick though in PyTorch. So in PyTorch, it works with the logits directly. So we have to first flatten our logits. So our logits have shape 2, 3, 50,257. And so we have to flatten those to combine those dimensions because the logits are expected, in our case, to be 2D tensors. So we do logits.flatten 0, 1. Let's call them logits flat maybe. And then logits flat.shape. And so we see we combined those dimensions. We just concatenated along this axis. And so we have now the 6 times 50,257 dimensional tensor. And so we can pass these logits flats and then the targets. So for the targets, we have to do the same thing. So for the targets, if I look at the shape, we have the 2 by 3, similar to how we combined the dimensions here to 6. we do it here too. So we do flatten. I think I just need one because there's only 2 dimensions. Let's double check. Yeah, so we combined those targets flat. And so here, what this is doing internally for the logits, it's internally computing the softmax probabilities. It's getting the correct probabilities according to the target token IDs. So it's getting them from here. That's why we have to provide the targets. And then it's computing the log probabilities, average them, and compute the negative, like the -1. And so it all happens inside here. And it's also optimized. So they have optimized function calls, PyTorch CUDA kernels. When you run this on the GPU, this will be actually faster than our manual implementation here. So let's see if we get the correct results. And you can see, yeah, we have now 10.79, which is exactly what we got before. But before, yeah, we had all these individual steps. Now we have combined it in one step. Okay, and so I hope this is making sense in some way. I know it's a lot of stuff that happens here. At the end of the day, I think all you need to know is that what we want to do is we want to make the probabilities of the positions corresponding to the target IDs as large as possible. So yeah, that is our goal essentially. Our untrained model will not generate anything useful. Our untrained model will generate gibberish, but at the end of the day, we want to train it such that it generates the correct tokens that we provide in the target tensor. So in the next sections, we will be working with this further and try to minimize this loss, which will then correspond to large probabilities in the correct positions.
Get this book at Manning.com.